Hi, so our lab this week, of course, was the scanning tunneling microscope. And I think everything is fairly clear now that everybody's been through the lab and collected data and everything. But there is one issue that's more complex than all the others, and that's this business of Fourier analysis of images with periodic lattices in them. And so I thought I'd talk about that a little bit. Not all of this is really relevant to this week's lab per se. It's more background than anything else, but still useful. The idea of a Fourier transform is very powerful and very widely used in all parts of quantitative science. So for those of you who aren't familiar with it already, hopefully this will be useful. So first of all, the basic idea is that if you have some sort of two-dimensional function, and an image, for example, is a two-dimensional function, right? Its intensity is a function of x and y position, then you can take a bunch of waves, and waves are either cosine functions or sine functions, and superimpose them on each other. In other words, add them all up. And you can do that with wave after wave, as many waves as you like. And the result is some general formula like this, a sum over as many waves as you like, each of which has its own wavelength and direction. And the result is always some complicated function in principle. And as I'll say below down here, where is it? Here's the theorem. Let me box that actually, since it's important. That any function, no matter how complicated, no matter how weird, can be represented as a superposition or a sum of waves like this. When I say a wave, so something like this function here, an amplitude A times a cosine function, and in the argument of the cosine function is a vector k dotted into a position vector x. What does that mean? Well, here's what it means. Here's the same function down here, k dot x. What that means is that the wave is traveling in the direction given by x, by k, sorry. So this is called a wave vector. And it gives the direction in which the wave is traveling, and that's pretty much clear. And then the length of the vector is equal to 2 pi over the wavelength of the wave. So if the wave is lambda, then this wave vector has length that's equal to 2 pi divided by lambda. And that means that features which have small wavelengths, short wavelengths, have large wave vectors, and things which have long wavelengths have small wave vectors. And that's important because a Fourier transform is a plot of wave vectors and amplitude, as we'll see below. All right, so as I say before, below or above, any function can be represented as a sum of waves. Let's see some examples of that. Here's a case where we have one wave that's traveling in this direction, in the x direction. It's got a wavelength of 5. We add to it with an amplitude of a half, right? This is an amplitude. This has got an amplitude too, but it's 1. An amplitude of a half over here for this wave. It's also got the same wavelength, but it's traveling in a different direction. And if you superimpose those two, so a full load of this stuff plus a half of this guy, then you get a pattern that looks like this. It's much more complicated than either of the two waves alone, and you can continue to add more waves and get more complicated things. Here's an example with 3 different waves. So again, one wavelength of 5 traveling in the x direction, another wavelength but shorter this time and traveling at about 30 degrees, actually about 20 degrees, to the x direction, and then a third wave which is traveling in this direction, or it doesn't matter, either direction, but along the same line. And it has a much longer wavelength, a wavelength of 22. Superimpose all those and you get this pattern. And you can see easily that as you start adding more and more waves with different wavelengths and different directions and different amplitudes, you can get very complicated patterns. Indeed, this pattern is already very complicated, And the question is, what will happen if you've got, let's say, 100 waves with different directions and wavelengths each and amplitudes each? And the answer is that with that many waves, you can draw a picture of the Mona Lisa, or maybe not quite the Mona Lisa, but you're getting there. And if you wanted to do the Mona Lisa, you just need enough waves. You can make any picture or any two-dimensional function at all as a superposition of two-dimensional waves. And in general, actually, you can make an n-dimensional function, a function on an n-dimensional space, a 10-dimensional space, let's say, if you use 10-dimensional waves and superimpose them. All right. Yeah, so with many waves, anything can be synthesized. Now, when we were analyzing our pictures from the STM, we did the reverse. We wanted to go find the waves that were present inside of a function. After all, if you've got a picture, and any picture can be composed of waves, then it follows that you can decompose that picture into waves. And so every picture has a bunch of waves inside of it, and those waves and their amplitudes are what we call a Fourier transform. So if I've got a wave which has two components, kx and ky, and there's an amplitude for the cosine wave and an amplitude for the sine wave, there's two different waves for each direction and wavelength in general, then I can try to find the actual waves so if this is my picture, for example, I can try to find the actual waves that went into this picture. Instead of making the picture from the waves, I want to find out what the waves are from the picture. And what would that look like? Well, it will look like something like this. Since there's only 3 different waves for this picture, that means my plot of this picture in wave vector space will have just 3 points corresponding to the wave vectors and the amplitudes of each wave. So I plot a wave in wave vector space. Here's the kx component, here's the ky component. And so this wave, for example, corresponds to this case because that's this wave. And this point corresponds to, notice it's got a very long wavelength, which means it's a very long wave vector, which means it's a short wavelength, right? So there's the short wavelength. That corresponds to this wave. Notice it's at 20 degrees, which is what this is. And then finally the third point, which corresponds to this wave, has a wavelength that's much longer, 22. Therefore, it's a short vector, and it's pointing in the minus 70 degree direction. So that's this angle here is minus 70 degrees. And notice also that the height of this dot, so this, you can think of this as being a spike pointing up out of the page here, each of these. This one's got a height of 0.7, this one's got a height of 1.0, this has got the greatest height, therefore it's making the biggest contribution, this wave is, to the picture. And then finally, this one's got a height of 0.5. So between the heights of the spikes and the positions of the spikes in wave vector space, in K space, this set of information, or this function, if you like, you can think of it as a function of kx and ky, is also a representation of the image above. And you can see that for some types of images, ones like this, the representation in K space is much simpler than the representation in XY space, and that's why Fourier transforms are often so useful. Very often, for the right kind of images anyway, the Fourier transform is a whole lot simpler than the original image was, and you can understand what the original image was doing by looking at the Fourier transform much easier than you can by looking at the image itself. All right. It is possible to show, and this is the actual definition of a Fourier transform, that if you want to find this representation of the image, even in cases where there's more than 3 waves, right? So 3 waves is simple, but let's suppose the image was composed of 100,000 waves, which can easily happen. Then all of a sudden this K-space image has 100,000 dots. It's not so simple anymore. How do you find those dots? How do you go from the image like this to finding the dots in K-space? And the answer is you do this double integral. You integrate over both x and y of your original function. This is your picture, multiplied or weighted by a complex exponential. I guess I didn't say this up above. I wrote it up above, but then didn't highlight it. A complex exponential has both the cosine waves and the sine waves contained inside of it. So the reason this works is because it's got the cosine wave and the sine wave contained inside of it. And the imaginary part of this function then contributes an imaginary part to the Fourier transform, and the real part contributes to the real part of the Fourier transform. And there's much more to say about this. This is obviously not a real overview of Fourier transform. We would spend a week or two at least if this were a class on Fourier transforms, but this will have to do for this class. So if you can do this integral, and there have been worked out over the years, over the decades, extremely efficient ways of doing integrals like this, and they're called FFT, fast Fourier transform. And you may have heard of an FFT or a fast Fourier transform before. And that's what the STM software does, for example. It takes a fast Fourier transform of the image and gives you back a Fourier transform which looks like the wave function in K-space. And from that you can tell some things anyway. It helps you to analyze what's going on in the image. All right, so that's sort of the mathematics of it all. What about our specific case? Well, in our case, without having the data myself, I didn't have any of you guys' data when I set this up, but without having the data itself, I can't talk about how to interpret any of the Fourier transforms you guys saw. But let's consider an ideal case. Let's consider just three waves, one that's traveling backwards along x, one that's traveling at 60 degrees, at 120 degrees really, and one that's traveling at 60 degrees, all with the same wavelength. Lambda equals, in this case, it's set up so that the wavelength is the correct wavelength to give the true, perfect, ideal STM image of a graphite surface, looking at every other atom, not every atom. And so if you superimpose these three waves, this is the image you get, and it is indeed a perfect hexagonal lattice. And it's an approximation to this that we're getting, hopefully, when we take an STM image. Here is the Fourier transform in K-space of this same image representing these three waves, and you can see there's one wave going this way, one wave going at 120 degrees, and one wave going at 60 degrees. And then each of them is doubled, so this dot and this dot are paired, that dot and that dot are paired, and so on. And the reason for the pairing is a little technical. I'll say it, and if it doesn't make any sense, don't worry about it. But the reason is that this is a real function over here. This guy has an imaginary part. In order to cancel the imaginary part, you need both k, the component that corresponds to k, and the component that corresponds to minus k, to have the same value, so that so this component plus the other one cancels the imaginary part of the Fourier transform, and you just get a real function. So the pairing here has to do with the fact that the image needs to be a real function. Again, if that doesn't help, don't worry about it. All right, so there's a hexagon of data points, and that gives rise to an ideal image from the STM. However, there is a catch compared to what we were looking at earlier, and that's the following. if my waves are pointing in the direction above, so one at 0 degrees, one at 120 degrees, one at minus 120 degrees, or 60 degrees is the same thing, those are not the directions in which the spacings between the closest nearest neighbor atoms occurs. That's the direction between the rows that are staggered from each other. In other words, it's this distance, it's that wavelength. And so the distances that you get out, the R period, that you read off of the display on the nanoscope, won't have the 2.46 angstroms that we calculate for the ideal spacing between carbon atoms, between visible carbon atoms in the STM image. Instead, what the spots will show, will correspond to, is a wavelength that's equal to the square root of 3 over 2 times the spacing between atoms. And so if the spacing between atoms is 2.46, then the wavelength, the ideal wavelength you're going to see in the Fourier transform is 2.13 angstroms, a little shorter because this distance is shorter than this distance. And likewise in the other direction. So the ideal situation, the R period for this dot would be 2.13 angstroms, and the same for this dot over here, and likewise for all the other dots as well. They would all have a period of an R period of 2.3 angstroms, 2.13 angstroms. All right, yeah, and that's what I'm saying down here, that the R period is the wavelength, but it's the wavelength for a wave that doesn't correspond to the distance between the angstroms, or distance between the atoms, the closest distance between the atoms. One last thing to say before I quit is that if you have the correct waves, and they're pointing in the correct direction, so 0 degrees, 60 degrees, and 120 degrees here, and same here, 0, 60, and 120. But their wavelength, their amplitudes are not all the same, so you have a different mixture of those waves. Then you get the correct wavelength spacings as before, but you start getting distortions in the image. It isn't this perfect hexagonal lattice anymore. Now you start seeing, well, atoms that look distorted, basically, and here's one type of distortion that can occur, here's another kind of distortion that can occur. And of course, these kinds of distortions are exactly what we do see in a lot of the Fourier transform, well, in a lot of the images that we've collected. So, and if the angles are off here, or if the wavelengths are off a little bit, then you can get even more distortions. And so what the Fourier transforms are showing you is how close your actual image is to the ideal up here. If you did have an ideal image, you'd get a perfect hexagon. The orientation of the hexagon, of course, can vary because the lattice isn't necessarily oriented the way I've drawn it here. It could be rotated by any angle whatsoever because the tip is just scanning over a piece of graphite. What's the orientation of the graphite in that spot? Well, it's random chance, right? We don't know. So, so the orientation of the hexagon may change and it still be a perfect lattice. But the spacings and the shape of that hexagon would be ideal if we had a perfect image. All right, I think that's all I have to say for now. I will take questions and talk a little bit about this again tomorrow.